Okay, let's do another example. One of my favorites is the long car in the skinny garage. Let's say that, and so what I'm picturing here is supposed to be a car and a garage, and I want to park the car in the garage. Let's say the car is 9 meters long, but my garage, for some reason, only built to be 6 meters long. Notice that I show that there is a door, what we'll call the front door, and a door that we'll call the back door in the garage, meant to just be a 3D rendering here. So we'll call this the front of the garage and this the back of the garage. Okay. So the question is can I fit the car in the garage? Right? If I try to fit the car in the garage, it doesn't seem like it'll fit. It'll stick out the front or the back or both. Okay. So the answer, of course, in terms of relativity is, well, I can fit the car in the garage for an instant if I drive it fast enough. Now, drive the car fast enough, it will length contract and it will fit in the garage. So the question is at what speed will the car fit in the garage? And you might ask, well, how's that going to help me? Because it's moving, right? We've got to be in an inertial frame or reference frame. We can't move it at that speed and then stop and expect it to remain that length. As soon as it stops, it's going to get longer again. So again, one thing to recognize is that this length contraction is a real thing. Things do really get smaller if they move at faster speeds. But when they stop, they'll get longer again. They don't stay smaller. The speed, the length of an object depends on its speed. And so if it's in its own frame of reference, it's always going to be 9 meters long. In a moving frame of reference, it's going to be shorter. So you might see a problem here, which is that the car will only fit in the garage for an instant. A moment later, it'll come bursting through the back door because it's still moving at speed v. Okay, but anyway, just for the heck of it, let's figure out at what speed it'll fit in the garage. Well, the proper length, we can just do this really referring to proper length, is 9 meters. The contracted length is 6 meters. We want it to fit in the garage. And we know that L prime is equal to L0 over gamma. So we can solve for gamma to figure out the speed. Gamma is 9 meters over 6 meters. Gamma is 1.5. And plug that into your calculator to find that V is 0.75 C. So I got a fast car. I can move that car really fast. I can make it small, fit in the garage. Okay, no, any problem with that? I mean, really, it is. Like, the car gets smaller according to the garage, so it can fit. If only for an instant. But then you start thinking, it's sort of like the twin paradox. It's a kind of a length paradox. We were doing this from the point of view of the moving car in the stationary garage, but you could just as well say that the car is stationary and the garage is moving towards it. So let's change colors just to indicate that, right? So we could change our frame of reference, make the car stationary, and the garage is moving toward it at V, and say, well, would the car fit then? That should be the same physics. It should be the same physics. Because whether the car is stationary and the garage moves, or the garage is stationary and the car moves, that's the same because all motion is relative. So it should be the same physics. Well, in that case, the car is stationary, so the car has a length of 9 meters, but the garage, so again, this is in the case where the garage is moving. The garage is moving, so while its proper length was 6 meters, it's going to length contract, right? So the garage is going to length contract by a factor of gamma. And we already figured out that gamma was 1.5. And so the garage is no longer 6 meters, but it is now 6 meters over 1.5, which is 4 meters. Wait a second. In that case, the car doesn't fit in the garage. So there does seem to be a paradox here. We say the car fits when the car is moving relative to the garage. We say the car doesn't fit when the garage is moving relative to the car, yet they should give the same answer. And here's the resolution to that apparent paradox. It's a question of what do we mean by fit? What does it actually mean for the car to fit? And the answer is this concept of simultaneity. that we're so wed to the concept of simultaneity that in order for the car to fit, what we mean is that the front of the car is at the back of the garage at the same time that the back of the car is at the front of the garage. In other words, for it to fit, the car must be like this, right? Looking at the picture. So the front of the car is at the back of the garage at the same time that the back of the car is the front of the garage. And we know it only fits for an instant because a second later it comes bursting through the back of the garage. So in order for it to fit, what we're saying from the orange point of view is that delta t, the delta t prime, right? In the orange point of view, the car was moving. Delta t prime is equal to 0 for the two events of front of car at back of garage and back of car at front of garage. So we said the time between those two events is 0. That the car is in the garage when those two things happen simultaneously. Well, remember that the time in a moving frame reference to that is going to be different. So those two things are not going to happen simultaneously. And this is what resolves the paradox, is that, again, if delta t is measuring the time between those two events, the front of the car is at the back of the garage and the back of the car is at the front of the garage, that those two things are not measured at the same time in the second case. And so there is no paradox, meaning, so from the car's point of view, looking at the car in a resting frame and the garage is moving relative to the car, what we see is that there's event 1. From the car's point of view, we see what's called event 1 happening when the garage is moving relative to the car and the back of the garage meets the front of the car. And event 2 is as the garage moves through the car, the front of the car meets the back of the garage, and that's event 2. And we know that the time between those two events is delta t. Whereas the time between those two events, when we looked at it from the garage's frame of reference, was delta t prime equals 0. Those two things happened at the same time. We know they have to happen at a different time now, hence the two things don't need to be the same size. And we can actually find the relationship by looking at the Lorentz transformation. So let's go ahead and look and see what the Lorentz transformation tells us. So let's just see. So if we're in the garage's frame of reference, right, which was that original frame of reference, which we called the prime frame of reference, because when we had switched it to make the garage move, we called it prime. So the garage frame of reference is the prime frame. And in the garage's frame of reference, the two events, front of car meets back of garage, back of car meets front of garage. In the garage's frame of reference, the car fits. So delta t prime equals 0. What is delta x prime? What is the distance between those two events in the garage's frame? Right, so in this picture here at the top, what is the distance between the two events where the front of the car is at the back of the garage and the back of the car is at the front of the garage? Again, let me be very, very clear. What is the distance between this event, the distance between this event and this event on this coordinate axis, right, delta x prime? It's the length of the garage, right? It's the length of the garage. So the distance between those two events is 6 meters. Now, let's look in the car's frame of reference. Here's the car's frame of reference. The garage is moving relative to the car. This is in the O frame, the car's frame of reference, what we ended up calling the O frame. In the car's frame of reference, we don't know how much time there is. They are no longer simultaneous. Event 1 and event 2 is no longer simultaneous, but we don't know what that is. But we do know the distance between those two events. What's the distance between this event of the back of the car being at the front of the car and this event, the front of the car being at the front of the garage being at the back of the car, according to the frame of reference attached to the car, right? So this is the unprimed frame of reference. According to the frame of reference attached to the car, this is the unprimed frame of reference. So this position right here is the position of event 1 relative to this origin. This position right here is the event 2 relative to, it's now at the origin, right? Because that's where our frame of reference is. So what's the distance between those two events? Delta x equals the length of the car, 9 meters. The distance between those two events is this right here, which is the length of the car in the car's frame of reference, because we're looking in the car's frame of reference here, this picture. So that is 9 meters. So sometimes these variables can be a little tricky to figure out. But anyway, so now we can figure out how much time it takes the garage to move through the car here, right? How much time it takes, that's this delta t using the Lorentz transformation. We know everything except for, oh, and we also know that v is equal to, what was it? V is equal to 0.75 c, or gamma equals 1.5. So now it's a pretty straightforward plug-in. We can use either equation, and we can plug into either equation and find that therefore delta t is equal to, just plugging in all the numbers below, 2.2 times 10 to the minus 8 seconds. Okay. That's the answer to the time between those two events.